When we think about chaos, we imagine some behavior whose outcome we cannot predict. It is tough to think of it as something which can be mathematically described. At some point, Galileo and Newton brought an idea that nature obeys unchanging laws which can be formulated in mathematical language. Therefrom, physical events can be predicted with certainty. Which all of it brings a raise to system which behave chaotically, and chaos theory. Chaos when the present determines the future, but the approximate present does not approximately determine the future. Edward Lorenz. So chaos theory concerns deterministic systems whose behavior can in principle be predicted. Chaotic systems are predictable for a while and then appear to become random. Well, unfortunately, no universally accepted mathematical definition of chaos exists. However, there is a commonly used definition, originally formulated by Robert L. Devaney. Must be sensible to initial conditions. Must be topologically transitive. Must have dense periodic orbits. I won't be talking about last two. But the very first condition, sensibility to initial condition, is another word, butterfly effect. Small changes have large effect.
We know that when a butterfly flaps its wing in Sheboygan, it can set into motion a chain of escalating gusts that eventually results in a hurricane in Bali.
Now let's consider systems which behave chaotically. One of those systems are nonlinear differential equation of third order. Here is a circuit which solves for function x. It has a significant delay for evaluating each point. We can switch between time series and phase portraits. Here you can see the attractor. Attractor is a set to which system is trying to evolve. As the result, it forms into this shape. This attractor is a phase portrait of one set of solution of the O described previously. Axis or function and its derivatives. This diagram is used to observe complex movement of the function. So how can we recognize a chaotic system? For that we have a Lyapunov exponent. Lyapunov exponent measures the average exponential rate of spreading of nearby trajectories, where if it is positive, it will indicate that the system is chaotic, and if it is negative, it will mean it is not chaotic. Common way to compute Lyapunov exponent is usually analytically. Few methods are proposed to do so numerically. One of them is Wolf algorithm, which I have failed to understand. Another one is Kent's algorithm, which I have used. Here is computed maximal Lyapunov exponents, where maximal Lyapunov exponent is the slope of the line in the right figure. On the left side is a phase portrait of collected data under certain conditions, for which Lyapunov exponent is calculated. This one has a very nice data. It has clear positive slope, which implies this data is chaotic. Some data seems to be finely identified as chaotic, but some, like this one, makes me think that algorithm I wrote gives me gibberish. Anyway, most data, it identified well if it is chaotic. Well, thank you for your attention. Push on the button below to subscribe.